Alright, so welcome to this video. We're going to start off with this example here. They want us to find the volume of a solid whose base is bounded by the lines y equals x and y equals the square root of x with the indicated cross sections taken perpendicular to the x-axis. And the first the first cross section that we're going to look at is squares, and then we're going to look at equilateral triangles, and then we'll do some semicircles at the end. Alright, so it sounds like there's a lot going on in this problem, but really it's not too bad. The first thing that I kind of want to do is maybe get a visual for what I'm actually talking about here. So they give us these two functions here, y equals x and y equals the square root of x. So what I'm going to go ahead and do is sketch those graphs here. So let me just go ahead and create my y-axis. So let's just call this, let's say that's y, and let's call that x. I'm going to go ahead and graph y equals x. We know that that's just a straight line, so this is going to be my blue curve, so that's y equals x. And then y equals the square root of x. Hopefully we know what that looks like, but let's just go something like that, a curve that goes like that. So that's going to be my green one. I'm going to say y equals the square root of x. Alright, so it looks like they're going to meet at some point. What I would like to do first, before I even begin the problem, is figure out, well, where do they meet, and figure out what my limits are. And the way I'm going to do that is I'm going to set these two functions equal to each other. So x equals the square root of x. Well, if I square both sides, then I'm going to get x squared is equal to x, right? So if I square this side and I square the right side, I get x squared equals x. I'm going to move this x that's on the right side over. So then I have x squared minus x is equal to 0. And if I factor out an x, I get that x is equal, or I'm sorry, if I factor out an x, I get that x times x minus 1 is equivalent to that. And then finally, this should lead you to say that x is equal to 0 and x is equal to 1. So that means that this part right here where they intersect is 1, and they meet at the origin. So it looks like they meet at the origin. Alright, so it looks like we got our limits, and now what I want to do is make a square, and then I want to place this square in this region. Sorry about that. Okay, so the region that I am talking about is this region right here. Alright, so in that region what we want to do is get a square. So let me just go ahead and draw a quick square. So let's say that this is my square. It looks something like this. Alright, so there's my square, and I'm going to add, I'm going to say this is delta x, my change in x. What I want to do, let me get a good color going on here. So with this side right here, so what I want to do with this side right here is I want to lay it such that it falls in my boundary. So I want to get a square this size, where this side S is really just this side right here, and I'm going to call that S there. Well, the key is well, what is S equal to, right? I can't just write S. I need to determine, well, what is S equal to? Well, S has a y value, so there's this one. Let's call this y equals the square root of x. Right? So whatever x is at this point, that's going to be the square root of that number. So if x is a half, then this is the y value, well, the square root of a half. Well, what's this y value right here? Well, that's just y equals x. So if x is if x is 1/2, then that's just 1/2. So how do you find the distance between these two? Well, you simply subtract. So it turns out that s is equal to the top curve, which is your square root of x, minus your bottom curve, which is just x. And we saw in the previous video that the formula for the volume of a square is equal to, well, it's just your limits of integration, so from 0 to 1, of s squared. But here our s is this square root of x minus x, and all of that is squared dx. And I'm going to go ahead and just say that that is good enough for me at this point. Again, all I care about up until this point is just setting up the problem. We've done so much anti-differentiation and definite integration in class that I am very confident that you can solve this problem from here. You just might have to, multiply this out, do some foiling or whatever you want to call it, and then go ahead and just find the antiderivative and then substitute your limits and you're all done. But that's pretty much it. It's just setting up the problem. And you're going to see in these three examples that these problems are really not that bad. Let's jump over to the equilateral triangle. Now for the equilateral triangle, so here's my triangle right here. Alright, so what I want to do with this equilateral triangle is I want to place this side, so let me do it here in orange. So I want to place that side again on this thing here. And so it should be coming out out of the picture, so out of my screen, so like a 3D image. Well, this side here is S, but again, what is S equal? We know that S, again, just your top curve minus your bottom curve. And that's pretty much it. That's all X is, or that's all S is, I'm sorry. So again, if you just remember the formula for volume for a equilateral triangle, it is the square root of 3 over 4. And then it's your limits. In this case, we're going to 0 to 1, and it's S squared. Well, what was S? Well, it's just the square root of X minus X squared dx, and we're done. Again, that's pretty much it. There's not much going on here. Again, you do have to crank out the limits, the integral, so you can actually find out what the volume is, but there's not much to it than that. In fact, you're just going to find out it's going to be the top curve minus the bottom curve squared. The only thing that will be changing, the only thing that's changing in these problems is just the constant that you're multiplying in front. Notice here the constant that we multiplied by was just a 1. Here the constant that we're multiplying by is square root of 3 over 4. And so let's look at the semicircle. Well, if you look at the semicircle, again, the formula for the volume is pi over 8, and it's the integral from a to b of s squared dx. Well, if you think about s again, s is just your top curve minus your bottom curve. So let me just move this down over here. So the volume is going to equal pi over 8, the integral from 0 to 1, and then s squared. Well, remember, s is your top curve, which is the square root of x minus x squared dx. And that's pretty much it. Again, the only thing, again, that's changing, if you notice, is just your constant in front, but everything else is staying the same. So again, just learn the formulas from the previous video, figure out what shape they're talking about, or what region or what type of volume they want, and then take it from there.